So, hello everyone. Today we will be discussing the chapter 6 of History of Mathematics, which is the Liber, Abaci, and Liber Quadratorum. So, the greatest mathematician of the Middle Ages was Leonardo of Pisa, better known by his other name, Fibonacci. So, now let us know who is Fibonacci. Fibonacci, also known as Leonardo Bonacci, Leonardo of Pisa, Leonardo Bigolo Pisano. He was born in Pisa about 1175, and he is an Italian mathematician. He was considered the most talented Western mathematician of the Middle Ages. As a young man, he traveled widely in the countries of the Mediterranean, observing and analyzing the arithmetical systems used in the commerce of the different countries. He quickly recognized the enormous advantages of the Hindu-Arabic decimal system. So, the Hindu-Arabic numerals. In 1202, Fibonacci wrote his famous Liber Abaci, or we called it Book of Counting in English. Arabic numerals not entirely new to Europe. Gerard had brought the system from Spain a half-century earlier; however, no book previously produced had shown by such a wealth of examples from every eld their superiority to the traditional Roman numeration. The Liber Abaci embodied virtually all the arithmetical knowledge of Fibonacci's time, including much Arabic science, and gave original interpretations of all this material. As the mathematical masterwork of the Middle Ages, it remained a model and source for the next several hundred years. And curiously, although the Liber Abaci circulated widely in manuscript, it was not printed in Italy until 1857, nor was it translated into English until uh, 200, 2002. So, although we have referred to our present number system as Hindu-Arabic, its origins are obscure and much disputed. The most widely accepted theory is that it originated in India about the 3rd century. So, in 3rd century BC, this is the numerals. So, as we can see, if the numerals we have today is different from these numerals. And the next important trace of numeral appears in curved inscriptions at Nasik, India. And in 2nd century AD, this is we called Brahmi numerals. The numerals used in the 8th century are termed Devanagari or sacred numerals. So this is the sacred numerals in 8th century. The outward appearance of the Hindu numerals went through a series of changes in transit from India, and the Arabs selected from the various shapes this most suitable for handwriting. And here in West Arab Gobar in 10th century, this is the Gobar numerals. And in Spain, 1976, it changes, and this is the numerals in Spain. The nine symbol, these are the nine symbols. And what is interesting is that during their long migration from culture to culture, the Indian number signs remained astonishingly constant in form. So as we can see, the 6, 7, and 8, 9 are same as the numbers we are using today. And so the Hindu-Arabic number system is the one which is used by other countries, and uh, usually now they are using it. So now we will go to Fibonacci's Liber Quadratorum. So if the Liber Abaci is the book of counting, the Liber Quadratorum is the book of squares. It is a book on algebra of Fibonacci. It was published in 1225 and it is considered Fibonacci's masterpiece. So Fibonacci compiled another work of note, the Liber Quadratorum, Book of Squares. Although the Liber Abaci contains a few Diophantine problems, the Liber Quadratorum is devoted entirely to Diophantine equations of second degree. In the dedication, Fibonacci related that he had been presented to the Emperor Frederick II at court and the one of Frederick's retinue, a certain John of Palermo. On the occasion, propounded several problems as a test of Fibonacci's mathematical skill. One problem required that he and a number for which increasing or decreasing its square by 5 would give also square as the result. It should be said that the problem was not original with John of Palermo, having having been investigated by Arab writers with whom Fibonacci was unquestionably familiar. So Fibonacci gave a correct answer, namely 41 and over 12. So that is the answer of Fibonacci in the numbers below. To find a number which, being added to or subtracted from a square number, leaves in either case a square number. Leonardo's solution of this, the problem which had stimulated him to write the Liber Quadratorum, is so very ingenious and original that is a matter of regret that its length prevents its inclusion here. It is not too much to say that this is the finest piece of reasoning in number theory of which we have any record. Before the time of Fermat, Leonardo obtains this solution by establishing the identities x squared plus y squared minus 4xy times x squared minus y squared is equal to y squared plus 2xy minus x squared. And as we can see in the below. So, excuse me. I, so, to find a number of the form 4xy times x plus y times x minus y, which is divisible by 5, the quotient being a square. So, let us take x is equal to 5 and y equal to a square such that x plus y and x minus y are also squares. The least possible value for y is 4, in which case, in the form in the number above, the 4xy times x plus y and x minus y. So we will use this. So 4, let us copy 4 here. Then we will multiply it to the x, which is 5, and to the y, which is 4. And the x plus y, uh, which is the 5 plus 4, is equal to 9. Then x minus y is equal to 1. And when we multiplied all those numbers, it will be equal to 720. That is the three squares in arithmetic progression where whose common difference is the congruum 720. So taking that x is equal to 5 and y is equal to 4, we will use the form y squared plus 2xy in another here, in another uh, here this y squared plus 2xy minus x squared is equal to 31, and x squared in the form x squared plus y squared is equal to 41, and the form x squared plus 2xy minus y squared is equal to 49. So the solution here is the 31 is the root of the first square, and the 41 is the root of the second square, and 49 is the root of the third square. So we use the value of x here and the value of y in order to answer the form, this form. So now we will go to Fibonacci's and square numbers. How can we find two squares that sum to a square? Leonardo answered this question in several ways, with the first method following from a simple observation that provides inspiration throughout the book. I thought about the origin, he stated that, of all square numbers and discovered that they arise out of the increasing sequence of odd numbers. For the unity is a square, and from it is made the first square, namely 1. To this unity is added 3, making the second square, namely 4, with the root of 2 is the sum. Is added the third odd number, namely 5. The third square is created, namely 9, with the root of 3. And the sums of consecutive odd numbers and a sequence of squares arise together in order. So let us see the 1. The 1 is 1 squared. The square of 1 is 1. And the square of 1 plus 3 is 2. Because when we add all the odd numbers, we can find its square. Like 1 plus 3 is equal to 4, and the square of 4 is 2. Then add another odd number. 1 plus 3 plus 5 is equal to 9, which is the square is 3, and 1 plus 3 plus 5 plus 7 will be equal to 16, and the square of 16 is 4. Then, so the general formula for adding all the odd numbers is 2n minus 1 is equal to n squared. So if we use that formula, we can know the squared of the number that we are adding. So for example, the next formula giving the square of 5 is obtained by letting n is 5 in the general formula. So we use 2n minus 1. We have 2 and our n is 5. So 2 times 5 is equal to 10. And we subtracted it by 1, it will be equal to 9. And when we add all the odd numbers from 1 to 9, like 1 plus 3 plus 5 plus 7 plus 9, it will be equal to 25. And so the square of 25 is 5. So that is our n, right? In the example, so a square of 5 is obtained by letting n is equal 5 in the general formula. So here, that is the Fibonacci's square numbers, that the sum of all odd numbers we can get uh, always we can get a square of all the sum of odd numbers. So that is the our discussion for the 6.2, the Liber Abaci and Liber Quadratorum of Fibonacci. So thank you and God bless.